6, deep learning, testing, and debugging. We have 5 excellent talks. The talks will be 12 minutes long, 8 minutes of talk and 4 minutes of questions. Please type your questions into the Slack channel, and please consider typing those before the speaker finishes so we can have a fast question time. So if the first speaker can introduce themselves, and away we go.
Okay, hi, can you hear me?
Yes.
Okay, great. I will get started then. Okay, so hi, my name is Brandon, and I'll be presenting my work about differential verification of deep neural networks. This is work that I did in collaboration with my lab mate Jingbo, my advisor Chao, and we are all from the University of Southern California. So by now, we probably all know that DNNs have achieved state-of-the-art performance in many tasks, such as image and speech recognition and autonomous driving, just to name a few. However, these models can be surprisingly unreliable. A very well-known example of this are adversarial inputs, where seemingly insignificant changes to an input can cause a drastically different output from the neural network. And in safety-critical systems, this is a huge cause for concern. So by now, there's many works that apply software engineering techniques like testing and verification to improve the reliability of neural networks. However, they're only designed to handle properties of a single network. And this is a problem because many of the properties we might want to consider are properties of two networks. For example, after the initial training of a network, we might apply some type of compression technique, or we might retrain it with some new data. And in these cases, we have an original network and an updated network. And this naturally raises the question of, does the updated network faithfully mimic the original? So current approaches are not designed to tackle this question. And it's an important question because we often expect the updated network to be functionally equivalent to the original in some respect. For example, in the case of compression, we expect the compressed network to perform identically to the original. So this brings me to our contribution. We built a tool called ReLUDIF, which is the first differential verification technique for deep neural networks. And in particular, ReLUDIF is the first tool that can prove the equivalence of two networks within a small error bound, which we call epsilon. So to give a comparison point, we adapted a single network verification tools to our problem domain. And compared to these tools, ReLUDIF can verify hundreds of properties that these tools simply can't handle. And in cases where both tools can handle the property, ReLUDIF is often up to 3 orders of magnitude faster. So for the remainder of the talk, I'll give an overview of the problem we aim to solve and how we solve it, and then I'll touch on our evaluation. So let's start with the overview. So we should define what a neural network is first. A neural network can be thought of as a mathematical function that takes as input real numbers and outputs real numbers. And it computes its output by taking its inputs and performing a series of affine transformations, followed by performing an activation function. In our case, we focus on the ReLU activation, which takes its input and outputs the max of 0 and its input. So the problem that we're interested in solving is given two neural networks, f and f prime, and an interval for each of the inputs to the network, which describes the input space that we're interested in. We aim to prove that the difference between the two networks for any input in our input space is bounded by epsilon. So I'll use a small example to illustrate why current verification tools fail to handle this problem and how ReLUDIF handles the problem differently. So on the left, we have an original network, and on the right, we have an updated network. And the main difference between the two is that we rounded the original weights to the nearest whole number, which are shown in red. And we're interested in proving that the difference in outputs between these two networks is less than 0.1 when x1 and x2 can take values between 0 and 1. So a naive way to approach the problem is to use an existing verification tool to compute the bounds. Current state-of-the-art tools are based on symbolic interval analysis, so we can use them to propagate symbolic intervals through the network, which will give us a sound lower and upper bound on the output of the network. And so we can use the tool to compute bounds for both networks, and then we subtract them. And this will give us a sound over approximation on the difference between the two networks. However, this tends to be pretty inaccurate. And the problem is that after propagating the symbolic intervals through the network, the final output bounds tend to have significant errors in them. And then when we subtract the bounds, the final result is often too loose to be useful. So the way we approach the problem differently is to compute the difference layer by layer instead of waiting until the final output layer to compute the difference. And this means that we do some of the difference computation before significant errors have accumulated, and this tends to produce significantly tighter difference bounds. Like previous work, we base our approach on interval analysis. So the way this looks is we'd start at the first neuron in the first layer, and we compute the difference to the input of this neuron. So for the first neuron, the only incoming edge weight that changed is the incoming weight from x2, which was reduced by 0.1. And since x2 takes values between 0 and 1, the min and the max difference in the input to this neuron is negative 0.1 to 0. Then we apply the activation function to this interval and widen it if necessary. Then we move to the next neuron and repeat the process. In this case, only the incoming edge weight from x2 changed. And since it increased by 0.1, the min and the max difference in input is 0 to 0.1. Then we'd apply the activation function and widen if necessary. And then after computing the differences for the first layer, we can use this result to compute the differences for the second layer and so on. But in this case, we don't have any following layers, so we just propagate these intervals to the output. And as we can see, the result is much more precise. In addition, we also implement a refinement procedure based on partitioning the input space into disjoint subregions. And what this means is that if there exists a proof, ReLUDIF can always find it. But of course, this is an NP-complete problem, so the runtime is exponential in the worst case. So that's a simple overview of ReLUDIF. However, the actual algorithm is much more involved, and I'll refer you to the paper for those details. So let's look at our evaluation now. We evaluated ReLUDIF on 3 popular machine learning benchmarks in the literature. The first is the Akashu family of neural networks for aircraft collision avoidance. And for the other 2 benchmarks, we train neural networks on the MNIST dataset for image classification and the human activity recognition dataset from UCI. And for all of the properties we consider, we took the original networks and rounded their weights from 32 bits to 16 bits. And then we chose an epsilon that would verify that the output does not change by more than plus or minus 5%. And in total, we created 842 properties. So again, as a comparison point, we took 2 state-of-the-art verification tools, specifically ReLUVAL from Columbia and Deep Poly from ETH. And we used
7 minutes.
Thank you. And we use them in the naive way described in the previous slides. And so the blue bar shows the number of properties verified by ReLUDIF, and the green and the yellow for the other tools. To summarize, ReLUDIF verifies 332 more properties than the other tools. And for the properties they both can handle, ReLUDIF is often 2 to 3 orders of magnitude faster. And as one more comparison point, we took a very large MNIST network with 4 layers and 4,000 hidden neurons, and again, rounded the weights to 16 bits like before. And then we took each tool and ran a single interval analysis without any refinement. So we did just a single propagation of intervals through the network and then measured the epsilon verified. And the table on the right shows the min, max, and average epsilon. And what we can see in the table is that ReLUDIF is on average 66 times more accurate than ReLUVAL and 12 times more accurate than Deep Poly. So that's everything I have. To wrap up, I presented ReLUDIF to you, which is the first tool targeted at differential verification. And in particular, the first tool targeted at proving the equivalence of 2 neural networks. So thank you for listening, and I'll take any questions now.
Thank you very much. So questions in the Slack channel or Slido? Okay, so after finding a fault, you have to fix something. So I don't know what it means to fix this in this sort of context. Any comments on that?
Yeah, I guess it depends on the use case. So like in the case of compression, that if they're not, the 2 neural networks aren't identical, that's actually a problem. So in that case, you'd want to like retrain probably. But if you say like you retrain a neural network with some new data, you want to add a little bit of new functionality to it. A fault in this sense might not necessarily be a bad thing. So I guess it really depends on the problem domain, because does that make sense?
Yes, it does.
Yeah,
yes, it does. Okay, I understand that you motivated the talk with the problem of the adversarial example, small changes that damages things. I understand all your examples were looking for differences in things. Are there other kind of properties you can look for?
Well, actually, that was just to motivate like the idea that neural networks are unreliable and have hidden behaviors. So I mean, we're not targeted really at adversarial examples necessarily. We're really looking at the case where you kind of like with software, you update software and then you want to verify that there's no new regressions introduced. So that's really how I see ReLU-Diff.
I understand. So looking at the questions, one question is, are there any compositional results here? Can you show that if things hold in, if property A or B holds, and then can you guarantee that it's going to be A and B holds without doing any further testing?
Ooh, I believe it's if A and B hold. So in this case, A and B would be like you have maybe 3 networks. You have like version A, version B, version C. I mean, in that sense, and like you prove A and B are equivalent, and then B and C are equivalent. I mean, in this sense, it's compositional in that sense. Like if you prove A and B are similar and B and C are similar, then yes, it's compositional.
That sounded like you not made up that answer, but that sounds like not a thing you'd been considering much in the past. So I don't think that sounds like an exciting area of future work, perhaps.
I hadn't really thought about this actually. So.
Okay. All right. Well, that's all our time. Please join with me in thanking for our speaker. And if our next speaker could jump on and introduce themselves.
Hi, team.
Yeah. Hey, Brandon, go.
Okay. Oh, hello, everyone. My name is Pinja from ETH Zurich, and I'm going to present our paper Structure Invariant Testing for Machine Translation. This work is performed with Clara Meister and Zhendong Su. Machine translation software such as Google Translate and Bing Microsoft Translator has been widely used in our daily lives. However, this kind of translation software will return translation errors that lead to unpleasant experience or serious consequences. For example, this is a German sentence that related to ticket issue on the website of Zurich Zoo. If you ask for Google Translate's help, it will give you an English translation. Children up to the age of 15 are given free admission to the zoo on presentation of a valid ID. However, if you follow this guidance, you will be refused to enter the zoo because there is a translation error. The correct translation should be on their birthday in the sentence. So this is a real-world cases that has led to unpleasant experience. And machine translation error can lead to much more serious consequences. For example, a Palestinian man was arrested for just posting good morning on Facebook because it was wrongly translated to attack them and hurt them. Thus, similar to traditional software, it's very important to have a testing technique for machine translation software. However, it is very challenging. First, most of the dataset, the label datasets, has already been used to the model training process. So the testing oracle of this kind of software is lacking. Second, one source sentence could have multiple correct translations. This further increased the difficulty of testing machine translation. To solve this problem, we propose a testing framework called Structure Invariant Testing. and its core concept is structural invariance. I will use a simple example to explain it. We can see that on the left-hand side, we have two similar sentences with only one word difference. And in the middle column, we can see the translation from Google in Chinese. They look similar too. And let's look at the third sentence. It's similar in its source sentence. However, its translations look quite different in terms of structure. And we observe that the first two translations are correct. However, the third translation is wrong. It means that I live on campus, I am tall. In this paper, we define structural invariance as follows. Translation results of similar source sentence should exhibit a similar sentence structure. Based on this core concept, our structural invariant testing framework has 4 steps. First, generate similar sentences. Given a source sentence, we will replace a word in the sentence by its similar words. For example, we will replace smart by cute and tall. In our implementation, we replace all the adjectives and all the nouns once at a time. For example, we replace people by students and professors. We use an NLP model called mask language model to implement this word replacement step. The second step is to collect target sentences. We input all the original sentence and generated sentence to any software that we want to test, any machine translation software we want to test, and collect the translation results. The third step is to generate representations of sentence structures. For each translations, we will generate a sentence structure representation. For example, we can have a tree-form structure representation. In our paper, we explore 3 structure representations: raw sentence, constituency structure, dependency structure. I will elaborate more on dependency structure. For example, given this sentence, its dependency structure looks like a tree and it captures the relations between different words in the sentence. For example, for the word systems and machine, their relation is compound because they can form a compound word. Last but not least, we will do error detection. For each of the translation structure, we will pair the just structure of the original sentence translation with each of the generated sentence structure representation and calculate their distance. After that, we will rank all the pairs according to the distance, and the one with the largest distance will be returned as the top 1 sentence. And this is what the results look like. We have an original sentence, and for example, the top 1 sentence that with distance 3. I live on campus with tall people. And this result indicates that either the original sentence or the source sentence or the top 1 return sentence has the translation error. And we have top K results. To evaluate our approach, we crawl the data set from CNN articles. We consider 2 categories, politics and business. Each one we randomly collect 100 sentences. We consider top K accuracy because we return top K results. It is the percentage of the reported issues where at least 1 reported sentence contains an error in top K. For example, for top 1, a true positive means that either the translation of the original sentence or the top 1 reported sentence is wrong. We test Google Translate and Bing Microsoft Translator. For both of them, we achieve around 70% accuracy, which is very high. And we collect 64 and 72 positives, respectively. Our approach can find 5 kinds of translation errors, and I will give an example for each of them. Under translation, if some words are mistakenly untranslated, we say that we say that it is an under translation error. For example, our motivating example on their birthday is not translated, so it is an under translation error. Over translation, we can see the example, a big step was translated to one a big step. So some words are unnecessarily translated multiple times. This is an over translation error. Incorrect modification, we can see the example, they remain members of privilege, becomes they remain privileged members. So this is an incorrect modification error. Word phrase mistranslation, we can see that in the example, amid a considerable large percentage of students was translated to agree unwillingly that a considerable larger percentage of students. So it is a word phrase mistranslation error. Last but not the least, unclear logic. If all the tokens phrases are correctly translated, but the sentence logic is incorrect, it is an unclear logic error. For example, I had a joke to tell and I wanted to finish it. It was translated to I joked that I wanted to finish it. We can see that all the words are correctly translated, but the logic is wrong. So it is an unclear logic error. So to summarize my talk, first, I introduce what is a translation error and why considering those errors is important. After that, I introduce the challenges of designing a test tool for this kind of software. Then we propose our structure invariant testing framework. And finally, I present our evaluation results with some examples. All the dataset and source code of this work has been released on the GitHub repository. Feel free to take a look. Thank you very much, and I'm ready to take questions.
Thank you very much. Please type your questions into the Slack channel, and we'll just wait 12 seconds for that, for the lag of any new questions. Very good. Very good. Your design has many intricate design decisions. How did you decide those? What is the closest system to this in the literature? And how did you know what to change from there to get to your current system?
Okay, thank you. For the design choices, for example, for the word replacement one, there are many NLP tools that can do this. For example, the basic word embedding or the mass language model we use. Actually, we try all of them, and because the mass language model performs the best, and actually it was the most well-designed technique related to this task, so we choose that. And we do similar things for other design choices. So we basically try all we can try and use the best one.
What was the runtime of this training sort of task? Is this CPU expensive?
The runtime for our testing tool is around 15 minutes for the Bing Microsoft Translator and 20 minutes for the Google Translate. And most of the time is used to it's used in the second step to collect the translations, because for each sentence, we need to call the API provided by those translation systems. And we believe that if you use the translation system designed by yourself, it will be much faster, and it is not CPU intensive.
Very good. Thank you so much. Please join with me in thanking our speaker for a great talk.
Thank you.
Now, Sherry, if our next speaker could introduce herself.
Yeah, can you hear me?
Yes.
Hello. So is everything good?
Yes.
Okay, great. So, hello everyone, welcome to my talk. I'm Jie Zhang. I'm a research fellow from UCL, and my topic is about automatic testing and improvement of machine translation. So translations are very important for people from different countries to communicate with different languages. But translations, they can be incorrect, and the problems can be quite serious. So for example, in history, the human mistranslations has once led to war. And for machine translation, such as Google Translate that Pinjia just introduced, there can be a lot more problems. And here are some examples that I Googled. I could call them machine translation disasters that have happened in China. So you can see that in the first photo, it's a Chinese menu, and the characters means roasted gluten, but the machine translation is roasted husband, which is pretty scary. So in the second photo, it's a warning to warn people to watch your step, but the machine translation is sleep and fall down carefully. So machine translations could have more problems, such as sometimes they're unfair. So here are some examples that I found in July last year. When I use Google Translate to translate the sentence, men do good research in computer science into Chinese. When it's men, the good is translated into very good. When it's women, the good is translated into a lot. And the same issue happens for male students and female students. And certainly the very good and a lot, they are quite different. And as a female researcher, I feel that such translation problems are very unfair. Although I know that the problems may exist in the training data, but still I feel very uncomfortable about them. So we call these translation problems inconsistency bugs. So how should we handle these bugs? So in traditional methods, when we do testing, we need the human oracle, which means the human translations, where we rely on a human translation and compare with the machine translation to test whether the translation is correct or not. And when there is a bug, when we do bug localization, we need to debug the training data and also the learning algorithm. When do the repair, we usually do model retraining with the training data augmentation or learning algorithm optimization. So these traditional methods, they are very expensive because of the human labeling process and also the model retraining process. And what's worse, they are not online, they are not real-time fix. So which means just imagine that a real user is now using the machine translation online. And if the translation is buggy, there's no way that these traditional methods could give real-time feedback and real-time fixing of the buggy translations. And as a result, the user may have to use the buggy translation without even realizing that it's buggy. Also, the repair part, the model retraining part is not bug specific, so which means when you retrain a model, you get new model behaviors. Some bugs may get fixed, but other bugs may appear. So in this way, other well-formed translations, they might be affected. So to tackle these problems in this paper, we proposed an automatic testing and also automatic repair approach for machine translation. And our approach does not use bug localization. It is cheap, fast, real-time, and also very flexible. So our approach has 3 steps. In the first step, we automatically generate test inputs, and we use a mutation to do the automation. So we would replace a word with its context similar words based on word vector similarity. And we also have a filtering process to remove the low quality test inputs. In the second step, we automatically generate the test oracles. And here we use metamorphic relation. And the assumption is that the translations on the unmutated parts of the sentences should remain similar. And we use consistency metrics in NLP area to measure the similarity. If the similarity is below some threshold, we would say that there is a bug. After detecting a bug, we use gray box and black box repair to repair the bugs. So due to time limits, because the test input generation and oracle generation, they are quite straightforward. So I would just skip them and just jump into the repair part. So once we have detected an inconsistency bug, we know there is inconsistency. But which translation is correct? There is also a probability that neither of them is correct. So to find the answer to this, we generate more mutants based on the original sentences and try to get the answers from these mutants. So for each mutant and the original sentence, we get their translations. We then do a ranking of them. So we rank them either by the predictive probability, or we just let different translations vote each other. So we use the cross-reference. So the translation that has the largest similarity with the other translations on the unchanged parts would be regarded as the best translation. And once we detected the best translation, we would combine this translation with the original translation and also think about the mutated word, use the word mapping to map back the translation, to change the original translation and get the final repair translation. So in this whole process, all you need is the translation output, where we call this a black box repair, or you just need the translation predictability to do the ranking. We call this a gray box repair. So for the evaluation, we use Google Translate, which is the most popular industrial machine translation, and also the Transformer, which is the well-known academia translator. And we design a separate research question for each step. So for the first step, we automatically generate testing inputs. So we want to know whether the automatically generate testing inputs, they are natural, they could simulate the real user input sentences. And our manual assumption indicates that our test input generation has an accuracy of 99%. And for the second research question, because we automatically generate test oracles, so we want to know whether these generated oracles could detect bugs. And we found that our automatic oracles have an F measure of 0.82 when detecting bugs for Google Translate, and 0.88 for Transformer. And also we found that either these automatic oracles or manual inspection reveal that Google Translate has about 36 inconsistent translations on the test inputs that we generated. So for the third research question, we do the repair. We found that black box repair reduces on average about 30% bugs for Google Translate and about 20% bugs for Transformer. And for gray box repair, because we don't have access to the predictive probability of Google Translate, so we just do experiments on Transformer, and we found that gray box repair reduces on average about 30% bugs for Transformer. So how about the efficiency? We want to know whether our approach could be fast enough to provide a real-time fixing for the users. And using our own machine, the average testing time is below 1 second. The average repair time is below 3 seconds. And we believe that for giant companies like Google, this could be speed up in a great deal. Okay, so to conclude, in this talk, in this paper, we introduced a black box and gray box automatic testing and repair approach for machine translation. And our approach requires neither the source code nor the training data. It is automatic, it is cheap, real-time, and fast, and also very flexible because it enables the repair of a specific bug without touching the other well-formed translations. And I believe that this kind of black box and gray box repair approaches could also apply to other machine learning domains, in particular other NLP tasks. That's all. Thank you very much for your time, and any questions are welcome.
Thank you. We'll just wait 12 seconds for any lag in Slack.
Great.
What was the oracle for question 1, the accuracy of the test generation?
Yeah, the oracle are the metamorphic relations.
Well, that takes us to the next question.
Oh,
Yeah. You may have said it and we just missed it, but can you speak more about the metamorphic properties that you applied?
Could you repeat your question? Sorry.
What metamorphic properties did you apply?
Fixed property?
What metamorphic properties did you apply?
Oh, metamorphic property. Yes. So we assume that because when we generate test inputs, we mutate the word, right? So for this mutant sentence, it would have a translation, and for the original sentence, it also has a translation. And for these two translations, we assume that the translations of the parts that excluding the mutated part should remain similar. Is that clear?
Very good.
So we use similarity metrics to measure whether they are similar or not. Yeah, thanks.
Okay. I did not understand the repair operators. Could you explain those again?
What operators? Sorry.
I'm sorry. I did not understand the repair operators.
Repair operators. It's for. Did you mean the mutation operators?
That's the question. I
understand. Yeah, my guess is that if you mean it's the mutation operator, we used similar ones for the text generation part, because here we generate more mutants and the rule is the same. So we would replace a word with more with its text context similar words.
So is this a post processor that takes the translation then fixes it? Do I have that right?
Yeah, you could call it a process. Yeah, we also use that term in our paper. Yeah, but I would prefer to call it black box repair because it's different from traditional software repair. What we want is the predictive behavior. So as long as we know the correct behavior, I mean, as long as we know what the correct behavior is, there's no need to do the bug localization for repairing the bug. So that's why I think it's especially, for me, it's very fantastic. It's very unique for machine learning repair. Yeah.
So one question we have here is, this seems all magical. Is all deep learning, is all neural, is all this stuff, is all testing this easy?
Thanks. I would assume that I would regard that as common as a compliment. It's not easy at all. Maybe my talk gave you the misunderstanding that it's quite easy, but for the repair part, it's quite complex. If you read our paper, you can find. But I mean, but the approach is quite easy to implement. That's true. Yeah. If we give a tool and it's quite easier for other people to use this.
Very good. So please join me in thanking our speaker.
Thanks very much. Thank you.
Very nice talk. Thank you so much.
Thanks.
Okay. And our next speaker is Yuan. If you have to stop sharing the screen, Gio.
Yeah, sure.
Please.
Sorry.
Okay. If our next speaker could share the screen.
Yep.
So I can hear you okay, and just waiting for the screen share to start. Very good.
Okay. Can you hear me?
Yes.
Okay. Hello, everyone. I'm Ziyuan Zhong from Columbia University. I'm presenting our work on testing DNN image classifiers for confusion and bias errors. DNNs have been widely used in many domains, but it has been found recently that it suffers from many different kinds of errors. For example, as being reported in BBC News, 2 Black people were tagged as gorillas by Google Photo app. Also, as has been reported by Business Insider, Google Photo also confuses between a scale and a mountain. DNNs also suffer from bias errors. For example, it has been found that DNNs tend to misclassify a man to be a woman if the person in the image is cooking. So developers want to identify these different kinds of errors before deploying a model in real world. So in this paper, we study these errors and develop a method, DPInspect, that can automatically detect these errors. And the setting we study is we assume we have access to a trained DNN model and unlabeled data. We study 2 types of image classification problems. First one is single label classification, and the second one is multi-label classification. The difference is that you can, for single label classification, you can only have 1 label for each image, but for multi-label, you can have multiple ground truth label for each image. We study 2 types of errors. The first one is called confusion error. For the single label case, it means that a DNN tends to mispredict class X to be class Y. So here, cellos misclassified as violins. For multi-label case, it's defined as a DNN tend to misidentify the class Y, or the Y is not in the image, but another class X is in the image. So in this example, although only keyboard is in this image, the DNN thinks that both keyboard and mouse is in the image. For the formal definition, we first define 2 types of confusion measures. Given class X and Y, we define single label confusion X and Y as the average of the probability for the DNN to mispredict one class to be the other. And for the multi-label case, is the probability of mispredicting the existence of both classes, given only one of the other class exists. And we refer both measures as arrow x, y in general, and we call a model has a confusion arrow on x and y if this arrow x, y is larger than confusion threshold. For the bias arrow, for the single label case, it's defined as the DNN is more likely to confuse between class X and class Z than class Y and class Z. So in this example, DNN is more likely to confuse between two types of monkey, langur and macaque, than langur and a screwdriver. For multi-label case, it's defined as a DNN is more likely to misidentify class X to be class Y than the reverse, given the presence of class Z. So in this example, given the scenario being on the door, women are more likely to be mispredicted to be men than the reverse. For the formal definition, we define a bias measure called confusion disparity as a difference between error between class X and Z and error between Y and Z. And then we define an aggregated value called average confusion disparity. That is the average of the confusion disparity of class X and Y over the third class Z. And we call a model has a bias error on X and Y if this aggregated value is larger than a specified bias threshold. Okay, so the question is, how do we detect the confusion and bias errors? Well, the idea is here we present is that for each class X, we find a good class level representation fx, such that we can use the distance between class representations to estimate the error between every pair of classes. And then similarly for the bias measure, we can take the difference between the distance over two pairs of classes to estimate this difference between two errors. Now the problem turns out to be, how do we get the presentation? How do we get this class level presentation fx? So in this work, we leverage the idea of neuron coverage. So we first define this PGI, which is a probability of each neuron J gets activated by inputs from a class I. And then we can form a class level vector denoted as a rho alpha I, which is vector consists of every neuron's probability gets activated from the input from this class I. For the experiment part, we evaluate our method on 8 models, our 6 data sets. We compare with 2 baselines. One is the random baseline, another is inspired by mode, which essentially is the average of each instance representation, and that representation is got by taking the output of second to last layer of the DNN. And then for the estimation, it's the same as our method. So the results we show here. So these plots AUC-EC curve, where the x-axis is the percent of pairs inspected by the DNN model, and the y-axis is the percent of the errors found. It shows that where the yellow curve is our method, it has a much larger area compared with the 2 baseline method. Also, if we inspect a threshold, it shows our method has higher precision recall. Similar trend holds for bias errors. In summary, in this paper, we define 2 types of errors for DNN image classification, confusion errors and bias errors. We develop a testing tool, DeepInspect, that automatically detects these errors for both single label image classification and multi-label image classification. Thank you for your attention.
Thank you for an excellent talk. We'll just wait 12 seconds for questions to appear in the Slack. We have one question already. Your design has many thresholds. Where did these thresholds come from? And what happens to your conclusions if these thresholds are changed?
Yes, indeed, there are different kinds of threshold. For example, here, this measure is called AUC EC curve. So this evaluates the performance at different threshold. So this shows a better trade-off of our method at a different cutoff of one of the threshold. So here the threshold is how do we define how rigorous we want to predict an example to be an error or not. And then another threshold is the threshold for defining the ground truth error. So for that threshold, we test two different kinds of threshold to basically show that our method work in general. Does that make sense?
Yes, it does. Other questions? Just waiting for any more. How long does it take to run your experiments? If I wanted to experiment with different thresholds, would that take very long?
It is very quick. We have released our code, and it depends on the data set. For most data sets, over 12 DP spec can run within like several seconds or several minutes.
Very good. And I'm not seeing any more questions. Is there anything else you'd like to tell us?
Not really.
Very good. Well, please join me in thanking the speaker.
Thank you so much.
Thank you very much for an excellent talk. And if you could stop sharing the screen, please. And last but not least, we have one more talk. If the speaker could, there we go. Just check your sound.
Hello.
Very good.
So should I start?
Yes.
Hello, everyone. Welcome you all to my presentation on repairing deep neural networks, fixed patterns and challenges. This work is done in collaboration with Rongit Pan, Jiang Nguyen, and Dr. Ridesh Rajan. We all know deep learning is being added to safety critical systems like autonomous driving, aviation system, medical diagnosis. However, DNN is bug prone. Prior works have shown different kinds of bugs in DNN. That's why this work studies the DNN bug fix patterns used by the developers so that we can inform automatic bug repair strategies. So we study what are the frequent bug fix patterns in DNN. Does fixing a DNN bug introduce a new bug? And what are the new challenges in fixing DNN bugs? With that aim in mind, this paper contributes a manually labeled data set consisting of DNN bug fix patterns from 5 most popular DNN libraries. We also propose a classification scheme for DNN bug fix patterns, and we study the new challenges in fixing DNN bugs. And we made the dataset publicly available for use. We started with the dataset proposed by Islam et al. At ISEC FC19. Out of the bugs we were able to collect 320 fixes from Stack Overflow and 347 fixes from GitHub for the 5 libraries. Then during the classification and labeling, first of all, a supervised pilot study was conducted to understand the classification scheme needed to label the bug fix patterns. Open coding scheme was followed to find the classification scheme, and we continued this process until we have a agreed upon classification scheme. Then the second and third authors are involved in labeling the bug fix pattern independently, and we are computing the agreement between the raters using kappa coefficient, and we found that the kappa coefficient was close to 90%, indicating perfect agreement. And the disagreements are resolved in the presence of a moderator, and finally we have a labeled data set of DNN bug fix patterns. We found 15 DNN specific bug fix patterns. A detailed discussion on those classification can be found in our paper. We have explored 5 research questions in this paper. For the shortage of time, I will briefly describe 3 of them. First of all, what are the most common bug fix patterns in DNN? We have found that the top 3 bug fix patterns in Stack Overflow are fixing data dimension, fixing network connection, fixing data type, and in GitHub, top 3 bug fix patterns are fixing versioning of different libraries, fixing layer dimension, and fixing network connection. Our key findings under these research questions are, we have found 18.8% of the bugs in DNN are fixed by fixing data dimension in Stack Overflow. An example is shown here. An input data of size 64 by 64 by 4 was converted to 4 by 64 by 64 to make the model to work. Next finding shows that when DNNs are fixed using resizing data, 63% of the time downscaling of the data is used. However, this has the risk of losing the robustness of a DNN model. An example is shown, a fix suggested by a developer in Stack Overflow. 198 by 150 pixel of data was downscaled to 150 by 150. Our next research question is, does fixing a DNN bug introduce a new bug? We have found, yes, it does. In this figure, the classification with old are from the bugs by Islam et al. At ISAKPC 19. And without the prefix old are the labeling we did in the fixes. And we have found 29% of the bug fixes introduce new bugs. An example is shown. The fit API of the Keras library was fixed by adding a parameter nb_epoch. However, this will throw exception in new versions of Keras as this parameter, this keyword does not exist. And another finding shows that API bugs have the tendency to introduce new bugs. We have found almost 38% of the new bugs are originated from API bugs, and almost 55.2% of them result crash. An example is shown in fixing convolution API. A developer has suggested to pass the filters using comma separated values 3 by 3. However, this will not work in new versions of Keras, as new versions of Keras expect the filter in the form of a tuple. Our next research question is, what are the challenges in fixing DNN bugs? We have identified 3 unique challenges. First of all, DNN reuse. A common tendency is to reuse pre-trained DNN model in different problems. However, this reuse can be harmful to the robustness of the model in the new problem, but the developers have no awareness that this is the issue going to be happening. Second challenge is the errors are not helpful in localizing the bugs. The errors always doesn't lead to the actual problem. And third problem, in DNN, a lot of libraries are interdependent. For example, NumPy, Pandas, TensorFlow, Keras, these are dependent. So updating one library caused some of the production codes to fail because the library is becoming compatible. Some of the related works to us, first of all, the ISAKPC 19 papers by Islam et al. They have studied the same 5 libraries. They have studied the bug types, root causes, and impacts. They have also studied the bugs at different stages of the DNN pipeline. And next related work is by Zhang et al. They have studied the bugs made by the developers who are using TensorFlow library. They have also pointed out some new challenges in fixing TensorFlow bugs. So in summary, I have presented our paper, which contributed a manually labeled data set of DNN bug fix patterns. I have also shown how we classified and labeled, and I have also presented some of our key findings. At this moment, I am happy to take if you have any questions. Thank you.
Thank you so much for finishing early. That's excellent. So we'll just wait a few seconds for questions to catch up on the Slack channel. And so we have one question. Can you please go back to slide 16? Didn't quite understand what you were showing there.
Slide 16?
Yeah. I think you flashed over it very quickly or something. I'm not quite sure.
Okay, this is the slide.
Okay.
So here, classification with prefix old are original bugs in the dataset by Islam et al. And we have collected the fixes.
What does it mean if there's a line between old IPS and AIPC? What does that mean?
So if I show old IPS, it introduced some bugs that can, in the fixes, it can introduce some APIC bugs, that means API contract bugs. It can also introduce some IPS bugs, that means parameter related bugs.
Oh, I beg your pardon. So I get it now. The fix introduces another bug. Fantastic. Okay.
Thank you.
Looking for other slides. Okay. Why do you think to change the data dimension in a bug? Shouldn't it be a user mistake because he or she is not familiar with the DN models?
So why do we think changing the data dimension is a bug?
Yeah.
So we think this because when the developers take a model from somewhere, maybe copying, and try to feed their data and try to train it, it throws exception at runtime. Then they have to step back and see where is the problem, and they have to do some image processing or using image processing tools to reshape their data, to resize their data, so that they can make their problem to work with the actual model. Some of the time, the developers reuse some existing state-of-the-art models to make their data compatible with the state-of-the-art models. They have to resize the data also.
Okay. Could you please go back to your chart of percentages of different kinds of bugs?
So different kinds. Which slide?
There was the distribution of different kinds of bugs.
Okay, sure.
Okay. Okay.
So
the question here is AI software different? Like if you talk about versioning and network connections, like how much of SE applies to AI?
How much of this fixes?
How much of software engineering applies to AI?
How much of software engineering is applied to AI?
Yeah. Like your network connections, is that network topology or is that network across some?
So network connection here, by network connection, I mean the structure of the deep neural network model. So a deep neural network can be seen as a connected network or graph of nodes and edges.
Okay.
So the condition is from layer 1, if the layer 1, it produces an output of dimension x by 10, the next layer should be able to take the 10 outputs. That means it should have some contract so that it can consume the 10 output layers passed by the previous layers. So if those are not matched, it can throw dimension mismatch error.
Okay, waiting for other questions on Slack. Nothing there. Do you want to talk more about future work?
So yeah, sure. There are a lot of future works to us. First of all, we obviously see we need automatic bug repair tools for DNN. And we have seen that lacking of debuggers for DNN. TensorFlow, Google has released a tool called Tensor Debug, but that's also very limited. We need to work on developing new debuggers, automatic bug repair tools. And also we need to develop a lot of program analysis tools for analysis of DNN programs. Yeah, that's all I have in mind at this moment.
Okay.
But I see a lot of.
Please join me in thanking the speaker.
Thank you.
And please join me in thanking all the speakers of this session who've presented excellent research and been kind enough to run exactly the time. And I hope you've enjoyed this virtual session at ICSE, and please stay around for an excellent session to come. Thank you all.
Hironori, please start.
Okay. Okay, so hello everyone. I'm Hironori Wasaki, working at Waseda University. So welcome to the session on Android and web testing. And so we have 6 talks. Okay, so our first speaker is George Mashu from North Carolina State University. The title is Slack Simian-based language agnostic code clones. So George, please go ahead.
Thank you, Hironori. Just setting up my screen. Can you see? Can you see Hironori?
Yes.
All right. Yeah. Hello, everybody. I am George Matthew. Today, I'm going to talk about Slack, Simian-based language agnostic code clones, co-authored by Dr. Chris Parnan, Dr. Katie Stolley, and me. So what are code clones? Code clones are snippets of code that are identical to each other. If these snippets have similar functionality, they're called behavioral or functional code clones. Consider the example of 2 interleaving arrays. Here are 3 Python functions that implement this functionality. The first uses an external library to chain 2 arrays. The second uses the inbuilt zip function that returns an element from each array. And finally, the third function uses the built-in range function. The first 2 functions have different syntax but exhibit identical behavior, while the second and third functions have similar syntax but exhibit similar but not identical behavior. You see, the first 2 functions fail to interleave arrays of different sizes, while the third function handles this case. The same functionality can be implemented in Java as well, as we can see on the right. Although the syntax of this implementation is different to all the 3 Python implementations, we can see it is still it has similar behavior to PyInterleave1 and PyInterleave2, and identical behavior to PyInterleave3. So why are code clones significant? For starters, most open source projects on GitHub have source code in 2 to 5 programming languages. This could result in similar functionalities across languages within the same repository. Thus, identification of functionality in one language in a repository can help a programmer replicate the functionality in another language. Further, a study by Mayer and others in 2017 found that an engineer who makes an open source contribution typically knows around 7 programming languages on average. And thus, knowledge of one programming language can help them learn a new language faster. This can also be applied in educational setting, where cross-language learning strategy is found to be the most common approach taken when learning a new programming language. Traditional code clone detection is limited to syntactic behavior and between similar languages like Java and C#. They are either based on predefined set of rules or an underlying embedding scheme like vector representation. As a result, it cannot be applied to languages that are drastically different to each other, like Java and Python. So we propose Slack, which is a clone detection tool based on input-output behavior, which identifies clones between partial and whole methods. Slack is also the first technique to detect code clones for a dynamic type language like Python. It does not require annotations or manual efforts such as seeding test inputs or input files. And unlike any other clone detection technique, Slack also detects semantically similar code snippets across multiple programming languages and type systems. Now we'll walk through Slack. To help us in understanding different phases, we will use the interleave example, which we described a little earlier. So in the first stage, Slack crawls through a repository and extracts source code. This can be from GitHub, Google Code Jam, etc. The next stage is segmentation. The source code is snipped recursively by extracting subtrees from their abstract syntax trees using a sliding window with a configurable size. Here we show 2 such subtrees from the AST of the interleave function. The extracted snippets are then converted into functions by identifying the arguments and possible return values. For statically typed languages, these can be inferred from the generated snippets, while for dynamically typed languages, these are inferred by data flow analysis of the constants present in the source code. The next stage is generating inputs for the snip functions. So inputs for Slack are generated using a gray box testing-based strategy based on the types of the function arguments. In case of primitive types, the inputs are sampled from a multimodal distribution, which is constructed from the constants of that type in the source code. While for objects, these are recursively generated for each argument in its constructor, which is expanded until it reaches a primitive type or a supported data type. Finally, once these functions are constructed and the inputs are generated, the functions are executed on these inputs in an isolated environment, and its return values and exceptions raised and time taken are stored. Then functions are clustered based on these generated inputs, executed outputs, and exception raised using a representative-based clustering approach. In this approach, clusters are built by a linear scan of the functions. So functions are only clustered in this case with the representative of the cluster rather than all the other functions in this cluster. This significantly reduces the runtime by almost an order of magnitude. So for the IntelliV problem, here are some of the clusters on the different submitted solutions. As we can see, the functions IntelliV and PyIntelliV3 are behaviorally clustered together since they functional identically. Also, PyIntelliV1 and PyIntelliV2 are clustered together since they're also functionally identical, but they only succeed in performing the IntelliV functionality partially. That is only in cases when the inputs are of the same length. This functionality can also be observed in the first loop of the IntelliV functionality in the Java code, and hence it's clustered along with these Python functions. That said, when the input arrays are all of the same length, all 4 functions behave similar to each other. Finally, Slack also managed to find other interesting clusters. Some of them are listed over here. So on the left are snippets of code that compute the area of the polygon. At the bottom, you can see 2 functions that read a file of integers. And on the right, you can see functions that find a minimum of an array. So these examples of clusters these are examples of clusters where you can associate some name to the functionality. There are other clusters also detected where it cannot be named or is a combination of multiple functionalities. Our experiments were performed on valid Python and Java submissions from the 5th round of Google Code Jam for the years 2011 to 2014. To benchmark, we compared Slack against Hitoshi.io, which detects Java clones at method level granularity in JVM-based languages using input-output behavior. Unfortunately, we did not find a functional clone detection technique for Python and cross-language clone detection. Hence, we compared it against an AST-based clone detection technique, which has been used as a benchmark earlier in other tools. To evaluate Slack, we used 2 sets of metrics. First was the number of clones detected in the corpus, and second was the precision of clone detection. So the precision is computed by running the detected set of clones on a new set of randomly generated inputs and checking how many of those clones held. Our experiments were executed on the Arc HPC cluster hosted by our university, NCSU. Based on our experiments, Slack identified 135 method-level clones compared to 20 by Hitoshi.io at 86.7% and 30.7% precision, respectively. So this was our first research question where we checked if Slack was successful in identifying clones in a statically typed language. Also, Slack is also the first technique to identify behavioral clones in a dynamic type language.
1 minute to finish.
We found that in Python submissions, Slack was able to detect clones with a precision of around 87.3%. Finally, the technique is also the first to identify cross-language clones between static and dynamic type languages at a precision of 94.2%. Based on the study, we can draw some implications. Firstly, it is easier to identify succinct behavior. This is because Slack identifies more clones compared to Hitoshi.io that operates only at the method level. And as we know, most methods encompass multiple behaviors. Next, we can achieve lower false positives by using more inputs as observed due to the high precision on Slack. For example, Hitoshi.io used only 1 test file while Slack used 256 inputs. And after 128 inputs, we observed a sharp decrease in the false positive rate for this dataset. That said, if inputs are generated by a random generation, we would need 4,096 inputs compared to 256 inputs required by Greybox input generation approach. Slack is still a work in progress. Post the XE work, we have actually extended support for pandas and library in Python and R language. We are currently working on expanding Slack from clone detection to code search by augmenting syntactic search with behavioral properties. Later, we do hope to expand Slack in other areas like translation of code on behavior and identifying differences in similar code snippets. Thank you for listening to this talk. You can read our paper on archive or feel free to please use and contribute to our work. Thank you. And I'm open for questions.
George, thank you for a great talk. Okay, so then we have several questions on slide. Okay, so yeah. The first question is, what are some applications of cross-language clone detection that you see?
Yeah, so I think for starting, we can actually look on a small scale when you think about the educational setting. So when somebody is trying to learn a new programming language, research has actually shown that the best way to learn a language is if they can find similar examples in a language they already know. That way they can actually map what they already know to the new functionalities. So if we can actually identify if how a piece of code can be written in another language using an example, that would actually help in learning. So this is just one such example of identifying clones. It can also be used for identifying candidates in program repair. And yeah, these are 2 applications I think I can think from the top of my head.
Okay, then one more quick question. Yeah. Do you think there are some language pairs?
I'm sorry.
Do you think there are some language pairs which are more difficult to analyze using Slack?
Oh yes, definitely. So even though we are actually identifying clones in Python and Java, which are different to each other, but still they have some definite structure to them, and they can be mapped to have almost the same typing scheme. But if there is a completely functional language, like say Haskell or something, this might be hard in such a case where it might be hard to infer the types and generate inputs in such a case. So I'm not really sure if it would scale to such a technique, but yeah, it is. I would say that it's still an open question, and we should be exploring that avenue later.
That's great. Okay, thanks again. Thanks to speaker, and also thanks to your audiences. Thank you very much.
Thank you.
Okay, then second speaker, please show up and please prepare your presentation. Okay, then second speaker is Rahul from University of British Columbia with his talk on near duplicate detection in web app model inference. Okay, so please go ahead.
Hello, everyone. I'm Rahul. Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Rahul, and I'm here to present my work, near duplicate detection in web app model inference, done in collaboration with Andrea Stocco and my supervisor, Dr. Ali Mesbah. So to start off, automated model inference is performed by web application crawlers, which explore the state space of a web page through UI interactions, and they generate a state transition model, which can be used to generate test cases to perform regression testing later on. After each exploratory action during the model inference, crawlers need to determine if a browser state seen on the browser is similar to any of the existing states in the model. Such comparison is challenging for modern web apps, where a potentially infinite number of similar looking states can be there. And these similar looking states are referred to as near duplicates in the existing literature. For example, here, these two states differ only by the name of one of the items in the list. And the name can be further changed to create more such states. Because of these near duplicates, if the state comparison used is designed to consider every change to be important, it produces inflated models. Or if it is too tolerant and considers every change to be insignificant, we end up with incomplete models. Both of these are suboptimal. And to find the balance between these two is the main focus of our work. Firstly, as there currently exists no consensus on what near duplicate states are, we developed a methodology to clearly define and characterize near duplicates from a functional testing point of view. To this end, we first mined state pairs from 6,000 real-world web apps. We then analyzed a random sample of these state pairs to label the changes and studied them. What we found was there are three different kinds of changes that do not impact functionality in any manner. The first category are the changes that are irrelevant to the functionality offered by the web app. These can be advertisements or background images that can change even without any user interaction being performed on the page. The second category are the near duplicates, which contain the same structure overall, but have different data. These are generally dynamically generated during runtime by applying data to templates. The third category can also differ in terms of overall structure, but the overall functionality remains the same. For example, if a new row is added to a table, which is of course semantically equivalent to other rows in the table, there is no change in the overall functionality. And as you can imagine, all these kinds of changes can be a direct result of exploratory actions during the model inference itself. Once we were able to find what functional near duplicates are, we wanted to see if any of the existing state comparison techniques can be suitable for their detection. We found that state comparison has been performed in three domains primarily. In information retrieval, it has been used to mine the broader web and get pages for appropriate content. And in computer vision, it has been used for plagiarism detection, or even mining and finding similar images. And in web testing, it has been used primarily to develop test cases or generate test articles. Overall, we selected 10 popular techniques from these 3 domains, and we adapted them for the purpose of detecting functional near-duplicate web pages. When we evaluated these 10 techniques based on the quality of web app models, we found that 3 differencing techniques applied on abstracted DOM were the best. What we mean by abstracted DOM is we remove the text content from the page and use only the structure of the web page. And the content hashing techniques were the worst, which is similar to the findings of previous study, where it has been used for mining data from the web and comparing web pages across web apps and not from within the same web app. Overall, the rest of the techniques, when properly configured, were able to produce models that are of comparable quality. In terms of performance, we found that complex visual techniques based on feature detection or structural differencing are not practicable for large web apps. One of the major challenges we faced during the study is the selection of optimal thresholds for which each technique can perform its best. And this currently is done by a trial and error process, and there are no systematic means available. In this work, we recognize that once a manually labeled data set is available, it can be used to select optimal values automatically. For example, here, these 3 bars show the distances computed by a technique for clones, near duplicates, and different state pairs respectively. However, the problem is that we found these thresholds to be dependent on the web apps used to create the label data. Therefore, for every new web app we want to test, or even for the different versions of the same web app, we have to create such manually labeled data, which is again cumbersome. Finally, after fine-tuning detection techniques, we analyzed the impact that different categories of near duplicates had on model inference. Recall that the dynamic data category near duplicates have no change in structure, whereas when there is data duplication, there is a change in structure. We found that the dynamic data near duplicates are easier to detect, and configured properly, most techniques can actually do a good job of detecting and removing them from the web app models. But when it comes to data duplication, we found that none of the techniques can detect them and remove them from inferred models. And to make things worse, data duplication is often a side effect of the state exploration itself. And the corresponding actions trap the web crawlers into infinite loops, and the final models are adversely affected as a result. This phenomenon was apparent in 3 of our subjects, where as time passes, the crawler only adds near duplicates and does not add any new states. And the overall quality suffers as a result. To summarize, our key findings are that DOM is the best state abstraction when textual data is removed, and there is no possibility of universal thresholds, which means that thresholds have to be configured for every app separately. And the threshold-based state comparison cannot remove certain kinds of near duplicates, making it ineffective for modern dynamic web apps. Our labeled data sets have been provided as artifacts for future research endeavors to improve model inference. Thank you.
Okay, thank you for your great talk. Then let's start a discussion. Okay, so we have one question on slide. So, and also some are more coming. So first question, could you please tell the usefulness of the near duplicate inference?
Usefulness.
Yeah.
So near duplicate detection is useful in our context, so that our models have only the states that contribute to the overall functionality of the web app. So if we have multiple states that have same functionality, we end up having inflated models. So by detecting them properly and removing them, we will be able to have models that have minimal set of states while showing the entire functionality of the web app.
Okay, great. Then one more question from slide. Is a state determined by only by the DOM? If so, did you run into cases where small changes in the DOM corresponded to bigger changes in other components?
Yes. There are multiple ways of looking at a web page. There is, of course, the DOM. There is, of course, the screenshot as well. But there are sometimes some more abstractions where only the text is looked at. And these abstractions have been used in different domains, which is what we collected in our study. And we tried to compare them, whether any of this abstraction relates to the functionality of the web pages itself. And that is our focus, where we want to have functionality we want to have a proxy to the functionality, which is a semantic concept. And these are all syntactic ways to look at a web page.
Okay, so thank you again. And well, although we have more questions, so you may continue discussion on Goguryeo. And so thank you again. Thank you very much. And then please, third speaker, come up to the stage and prepare your presentation.
Can I start now?
Yes, okay. So third speaker is John Cho, and his talk is titled JS Identify a Hybrid Framework for Detecting Plagiarism Among JavaScript Code in Online Minigames. Okay, so please go ahead.
Hello, everyone. I'm Zhongzhu Zhou. Today, I'm going to talk about our work done during my internship in Tencent's WeChat. JS Identify a hybrid framework for detecting plagiarism among JavaScript code in online minigames. First, you may wonder what are online minigames. Online minigames are lightweight game app typically implemented in JavaScript running inside another host mobile app, such as WeChat, Baidu, and Alipay. In China, almost 1 billion people have played WeChat's online minigames, dominating 71% of the population of China. Essentially, online minigames are HTML5 games without DOM, CSS ever, but they run inside another app. Let me show you the running screenshot of online minigames. We can see the WeChat mobile app on the screen. First, we click WeChat. Then we can see lots of online mini programs and game on the interface. Then we click the We Going game, and it's a spaceship game. And you can see the game in the video now. And the infrastructure of online minigames is based on JavaScript code. We can see the We Going code example on the left. Then the code will go through the VA engine embedded in WeChat and its interpreter Ignition. Ignition will generate the abstract bytecode as shown on the right. Because of huge number of users in WeChat online minigames, this game have great profits. 43 games against tens of millions of Chinese yuan amounts, causing the online minigames to be the target of plagiarism. In 2018, tens of code plagiarism happens in a day, and there are 21% plagiarism games among online minigames. This plagiarism can have a negative impact on a fair, profitable, and healthy game ecological environments. And therefore, we need to fight against these plagiarism games. In WeChat's repository, there are 4 common plagiarism types. The code example on the left is the find_make function as the original code. The code example on the right are 4 types of plagiarism example for find_middle. And type 1 is the identity code except change in whitespace or comment. And type 2, the plagiarist change code in name cases, replacement of identifiers with expression. Type 1 and type 2 are easy to detect. And type 3 clones are additional deletion of rounded code fragments and gapping. And type 4 clones are advanced obfuscation operations such as control flow flattening, nested function, and string array encoding. For example, we can see the button on the bottom of the right of the plagiarism add the wrapper function to the original function and use ASCII and hex to decode the original code. Overall, type 3 and 4 clones are hard to detect eventually. Therefore, we designed the JS Identify framework, whose overview is shown on this slide. A developer submits a game to the WeChat backend. The filter will preprocess the game code and generate simplified code and bytecode. The scheduler then calls the detection technique one by one. Once the detection technique has detected plagiarism, the JS Identify stops. The order of the techniques is decided based on the detection gain. The detection gain is designed to give priority to lower cost and more effective techniques. Then the judge will decide the plagiarism based on the similarity generated by these techniques. In JS Identify, we abstract the general process of computing game similarity. First, we define the unit of comparison of 2 games. For example, the technique can choose function or the whole game as the units, and then the technique needs to aggregate the unit similarity to the two games similarity. I'd like to introduce winnowing pass first. The first technique unit on the comparison is the whole game. The technique uses winnowing from the well-known MOS tool for plagiarism detection, but we found that it's difficult for MOS to detect the type 2, 3, and 4 clones. Therefore, our main contribution in winnowing pass is to pre-precise the code before applying MOS. For example, the original code is shown on the left. The plagiarists add an array and a function to represent the variable name. This plagiarism belongs to type 3 clones. After we pre-process the code, we attend the result on the right. We have done these 3 pre-processing steps before applying winnowing. The second technique is the swing technique. We found that it's challenging to detect type 3 and 4 clones. In the swing technique, we use bytecode, a lower level representation that will not be influenced by changing from type 1 and 2 clones. We first compute the function similarity and aggregate the function similarity to the game's similarity. We use a weighted flow network to aggregate the function similarity. We want to let length of code from a function as the flow into another function. Thus, we use the weighted flow network as the aggregate technique. It can detect rounded code on the left. Huge similarity can result in more flow from a game into another. Also, if the plagiarism splits a function into several functions, the technique can also generate a large flow as shown on the right. The high-level overview of the swing technique is shown on this slide. We define the graph capacity as LCS between the function. We define the weight of the weighted flow network to indicate whether a function can be embedded into another function successfully. You can find more details of the swing technique in our paper. Plagiarists may change code really differently, but they typically are not able to change the sign or game model substantially. Thus, a plagiarism game has similar sign and controller as the original game. A game is made of multiple signs. A sign is a user interface of running a minigame described by a same tree. Each node in the tree represents runtime data such as position and invoked method of a component like the UI controller, sprite, and action. We construct a bipartite graph, computes the match size tree of the two games, and aggregates them to the whole game similarity. We also conduct some evaluation for JS Identify. First, we evaluate JS Identify for general JavaScript code. We choose master.js as our experiment subject. We can see the red frame in the table, and JS Identify reports the highest similarity level. 4 clones are higher than 19%, and 2 are around 18% for all the 6 synthesized clones. Then we want to evaluate its performance on online minigames. We randomly select 100 pairs of plagiarism games in the WeChat repository of plagiarism games. Then we select 200 non-plagiarism games. The right circle shows the available place of JS Identify, and we set the final threshold as 85% in the production environment. We can see that JS Identify achieved the best effectiveness and still achieved relatively high recall with a high threshold. High recall indicates detecting more plagiarism. In addition, we evaluate the best F1 score results and the average time consumption. JS Identify has the highest F1 score. Although the detection time is non-trivial, it's still reasonable in WeChat application setting. Finally, let me introduce our deployment experience in WeChat practice. During 11 months of deployment, JS Identify has performed 1.5 billion comparison among 200,000 game versions for tens of thousands of online minigames. JS Identify detects 21% plagiarism games in 2018, and currently JS Identify helped reduce to 4% plagiarism games. But plagiarists continue to obfuscate for code for further attempting to escape the detection. Detecting plagiarism code in JavaScript is still a long-standing challenge for our ongoing and future work. In summary, we have presented JS Identify, a novel framework for detecting plagiarism cases in WeChat online minigames. We have illustrated 3 JS Identify techniques proposed based on different levels of code abstraction, and our evaluation results show that JS Identify outperforms other existing related approach and achieved the best performance. And thank you for your listening, and you can check our paper for more details, and I'm glad to answer any question you may have now. Thank you.
Thank you very much. That's a really great talk. And okay, so let's start discussion. And so first question on slide, so will code obfuscation influence your approach? And it seems that it is quite yes, right? And yeah, please, can you answer this question?
Sorry?
Will code obfuscation influence your approach?
Obfuscation in what? Sorry?
affect your approach?
The obfuscation in our codes?
Well, I'm not sure about the meaning of that, or intention, but perhaps, yeah, there will be various, different code obfuscation approaches, right? So,
yes, there are a lot of types in the code obfuscation, and you can see this slide. We have listed 4 types of plagiarism obfuscation types: type 1, type 2, type 3, and type 4.
Great. And actually, I have a related question, my own question. Okay. So today you show us the details of the detection technique, right? So
yes.
Then some malicious developers or plagiarists may try to avoid such detection technique.
Yes.
So what you will expect next, or?
Yes. The plagiarism continue to obfuscate code for escaping from our detection, and we have three techniques to protect the code. And my colleague Zhihao Li will introduce some work in Tencent now.
Hello. Let me answer this question. We do 2 things to resolve this problem. Firstly, we compress the code variable name to 1 character, and we will evaluate and replace the constant experience, and remove the space and the data code. And secondly, in addition, we have done something more challenging, because after JS obfuscated, it is abstract. Its abstract syntax tree structure may be changed very much, but after deeply analyzed, it is found that no matter how it's obfuscated, we will find its tree name will not be changed. Yes, it will be stable. Yeah, so we just need to calculate the hidden tree name, and we use is our fingerprints to represent the code fingerprints. And after the 2 points, we will resolve it. Yes.
Okay, great. And so one more quick question from slide. So can you comment more on how are the code plagiarism tools conceptually different from JS Identify?
Comment more code plagiarism in JS Identify?
Yeah, there are some other similar tools, right? So
yes.
How you approach and other tools are different?
Our approach is a hybrid framework. Other technique is only use one technique, or use several basic technique, and our framework use several big technique like the winnowing plus and swing technique, and the sign tree. And our each technique has their own different level of code abstraction in our framework, and this is different. And we construct a priority list in the JS Identify to do the detection. We let the last time and high effective technique in the first, and it can save our time to detect the plagiarism in the WeChat online minigames, because we know we have a large size in the WeChat online minigames, about 200,000 game version of a lot of games. So other approach may have a great quality, but they consume too much time in their detection. Yeah.
Okay, great. So thank you for a great talk and also great discussion. And so audiences, if you have more questions, so please continue discussion on Crowder. Okay, so thanks again. Thank you very much.
Thank
and
you.
Then let's welcome next speaker. Okay, next speaker is Jae-Shan Chen from Australian National University with the title Unblind Your Apps, Predicting Natural Language Labels for Mobile GUI Graphical User Interface Components by Deep Learning. So please go ahead.
Can you hear me?
Yes.
Hello, I'm Jae-Shan Chen from the Australian National University. Today I present our paper Unblind Your Apps, Predicting Natural Language Labels for Mobile GUI Components by Deep Learning. My co-authors are Chunyang Chen, Zhenchang Xing, Xi Wei Xu, Li Mingzhu, Guoqiang Li, and Jingshui Wang. The smartphone is become a necessity in our daily life. Having millions of mobile applications from Google Play and App Store, we could easily access a wide variety of services using the mobile applications. However, many applications remain difficult or impossible for people with disabilities. According to the World Health Organization, it is estimated that approximately 1.3 billion people live with some form of vision impairments. For these people, they would be more eager to use the mobile application to enrich their lives. So it is very crucial for us, for the researcher and for the community to take some action to help them to access the mobile application. The smart platform have developed a software called a screen reader to help them to access the mobile application. Here is an example.
Settings, toggle, double tap to activate. List. Welcome back. You haven't tracked time for a while. Unlabeled. Button. Double tap to activate.
As you can see from this example, the screen reader allows the user to explore the views while audibly describe what's on the screen. For this text element, the screen reader could easily read out the text. However, for this image-based button, the screen reader could not directly read labels from images. It instead reads the content description set by the developer in the source code. If the developer do not set the content description, for example, for this bottom right button, the screen reader would read unlabeled, which do not expose any functionality to the user. Without this label, the blind people have to try and guess the functionality of this image-based button, and they would eventually end up using this application. So how to set the content description? Here is an example. For this image button, the developer would add a reference to the Angel content description in the layout XML file. The actual value is further referred to the resource file, which contains shared labels for this image-based button. Therefore, we decided to conduct a motivational mining study to evaluate the current status of accessibility issue. We crawled about 10,000 Android applications from Google Play Store and obtained the screenshot and corresponding XML runtime code. The runtime code contains bounds type and content description for all elements on the user interface. To our surprise, we find that more than 77% applications have issue of missing labels. It seems that the developer may not care about the content descriptions. In details, more than 60% user interface have accessibility issue. Imagine you are using the application, and for every 2 user interface, you will encounter at least 1 image-based button which you do not know the functionality, it is very annoying. Here shows the distribution of the category of the application with different missing rate. The purple bar indicates the number of applications with over 80% missing rate. As you can see from the chart, among all categories, at least 30% of applications have severe problem. We also evaluate the correlation between the installation number and the missing rate, as we expect the popular application would care more about the accessibility issues. Unfortunately, the results indicate there are only a weak relationship between these 2 factors. As a conclusion from our motivational mining study, we conclude that the current accessibility issues are serious, and it is common among all categories and all applications with different popularity. And even though there are many accessibility guidelines given by the mobile platform, the developer may not care about the accessibility issues. Therefore, we propose a method called Label Joy, which could complete the labels of image-based buttons for current applications with minor efforts and assist the developers in efficiently filling in the content description of image-based button. Here is our approach. We take as input the image-based button and feed it into the convolutional neural network to extract the image feature. And then the feature is fed into the transformer encoder module, which models the relationship between any 2 input vectors. For the decoder path, it takes 2 inputs, the previous output tokens and the potential from the encoder module. And then it outputs the probability of the next word. So therefore, for this image-based button, we predict open navigation drawer. Here is some example for our dataset. We clean the data from the empirical study and obtain about 20,000 image-based button and the content description. We consider 2 research questions regarding accuracy and generalization and usefulness. For the accuracy evaluation, as you can see from this table, our method outperforms in all metrics and gains about 2% to 11.3% increase. Here shows the performance of our method among different categories, which indicate that our model is robust to apps from different categories. For the generalization and usefulness evaluation, we select 12 applications with 100% missing rate, resulting in 156 image-based buttons. We invite 3 annotators to create label for this button and 1 evaluator to rate these labels using the acceptability score. Here is the result for the evaluation. From left to the right, shows the box plot for 3 annotators and our model. It indicates that the quality of the content description of our model is higher than that from junior Android app developers. Here is some example, and we conclude 4 reasons when the labels from the developer obtain a low score. The first one is some developers will tend to create long labels which are too verbose. The second one is the developer would instead create too short labels without enough information. And the third one, they will sometimes create ambiguous label which may confuse the user. And the last one is that the developer would also make mistakes. All of this observation indicates that the developer may not be aware of how to add concise and easy to understand description, while our model could efficiently help them to do this. For our future work, we would like to consider to take the app metadata into consideration, as we observe that one image-based button may have different labels in different contexts. And the second one is we would like to test the quality of existing labels by checking if the description is concise and informative. That is the end of my presentation. Thank you for your time. And I'm happy to answer the question.
Oh, that's great. Thank you. Thank you very much. And that's a really great talk. Oh, and I forgot to mention that this paper receives ACM SIGSOF Distinguished Paper Award, right? So yeah, congratulations. Okay, then we take some questions on slide. Okay, first question. Does your method possible to test obfuscated app?
Sure, because we obtain the runtime code from the app directly, and the obfuscated will not obfuscate the content description for this data.
Okay, great. Then second question on slide. Is your raw data set of screenshots and the corresponding XML files publicly available?
Yes, we released the data set of the pairs of image-based button and the corresponding content description. If you need more metadata, we will release the rest data set.
That's great. We have a few more minutes. Okay, I'm curious about reinforcement learning in your case. Can you, yeah, because image captioning is essentially sequential prediction task, and so recent advances in image captioning have used reinforcement learning, if I stood correctly. So.
Do you mean that do I ever consider use the reinforcement method in our
Well, task? You may compare, or you may, maybe in the future, you may incorporate, or do they have some comment on that?
No, I don't. I think that reinforcement learning is should have a clear task, while our method, while the labels from our model while the labels for our dataset is diverse and cannot be standardized.
Okay, I see. I think, yeah, we have some more time. So audiences, if you have more questions, then please type your questions on slide. Well, okay. So one more quick question. So your approaches can be also applied to any desktop or web applications?
Yeah, if we can obtain the data set, we could use our methods in all kind of data.
Okay, great.
The key point is to obtain the pairs of image-based button and corresponding content descriptions.
Right. Okay, I see. Okay, so that's a really great talk and also very great discussion. So thanks to talk speaker. Thank you again. Thank you very much. Okay, then we will have two more demo papers. Okay, then next paper is titled Droid Mutator, an effective mutation analysis tool for Android applications, and the speaker will be Zhang Liu from East China Normal University. If this is correct, then please start to play the video.
Droid Mutator, an effective mutation analysis tool for Android applications. Droid Mutator consists of three parts: Mutator, Builder, and Launcher. First, the Mutator is used to generate mutants. Now, run Droid Mutator. We can choose one or more mutation operators to apply the selected source files. And we can check the difference before and after the code mutation. Mutator can control the scope of the mutation operator. The default configuration is that the mutation operator modifies all the operations that can be modified in the source code file. By modifying the configuration file, we can control the scope of the mutation operator. Here, the configuration mutation scope is in the onCreate method. Now, we repeat the last steps. Mutants generated at this time is only in the onCreate method. Then Builder can package each generated mutant file into an APK file. For build each mutant as an installable file. Finally, Launcher can automatically install and run APK files. Now, install and launch applications. This step can be used to identify some mutants that will crash at startup. These mutants do not need to be at last. Thank you.
Hi everyone. In this presentation,
okay, so we had a really great demonstration. So thanks to the speaker. And so if you have any questions, audiences, please start discussion on Crowder. And okay, then and final demo paper is titled Big Test, a symbolic execution-based systematic test generation tool for Apache Spark. And the speaker is Muhammad Ali Garza from University of California. Okay, so could you please start video?
Hi everyone. In this presentation, I will give you a brief introduction of our tool called Big Test that automatically generates test suite for data flow programs. Big data applications are prevalent in almost every production software today. They process large-scale data to extract valuable insights. While testing for traditional softwares have matured over the past 2 decades, testing for data flow programs is still in its adolescence. And the reason behind this is that these programs have relational skeleton, which is backed by hundreds and thousands of lines of code. They also have complex user-defined functions, which contain complex string operations, as well as unbounded collections, which are really hard to model symbolically. So the question is then, how do we test these applications effectively and efficiently? So what are we doing today in terms of testing these programs? Normally, we download a small sample data on our local machine and then test the program on that small sample. However, using a small sample means that we cannot exercise all the paths in the program. And if we increase the size of sample, that kind of defeats the purpose of sampling in the first place. On the other hand, traditional software has tools for automated test generation which are very effective and are based on techniques such as symbolic execution. However, in big data applications, each data flow operator is backed by several hundreds of thousands of lines of code, which is not feasible to model through symbolic execution. So to overcome the limitations of both of these approaches, we designed BigTest. BigTest takes in a big data application as input, and it generates a suite of test data that provides really high test quality. Internally, BigTest splits the data flow program into a list of user-defined functions and a list of data flow operators. For user-defined functions, it performs symbolic execution on those functions. For data flow operators, it models the semantics of the implementation of data flow operators in first-order logic, and then use it in tandem with the symbolic representation of user-defined functions to represent the entire program in a symbolic form. Once we have that symbolic representation, we give it to a CVC4 theorem solver or Z3 theorem solver and generate test suite that provides really high test quality. Let's see BigTest in action on a sample program. Here we have the source code of the application that I have shown you in the slides. Once we run BigTest, you can see the progress of BigTest in the console log window, as well as the progress of symbolic execution on each user-defined function. And here you can see all the path constraints and the corresponding data generated by the theorem solvers. Finally, each of these test data can be used as input to the test function for this program.
Okay, so as we see that we had another great demonstration. Okay, so actually that's it. So in this session, we had really great talks and demonstrations, and also we had really productive and very active variable discussions. So our big thanks go to all speakers and also all participants. So once again, thank you very much. Thank you for coming. And I hope you will enjoy the rest of the conference. So thank you very much.